context is P1. So P1, only P1 is in the ready queue. So P1, P1, P1 until it is terminated. So this is a round robin one. So round robin is the best response. In terms of response time, is the last one. Okay? So that is the round robin. Some of the operating systems use the round robin like always the fixed amount of time. For in this case, quantum 4, 0, 8, 12 like that. Because you don't want to take care how long it takes. Always the fixed. But at that time, the disadvantage is there might be unused waste of the CPU time. But it's much simpler. So that is the round robin, the CPU scheduling algorithm. Okay, so this is another example with a time quantum 20. So time quantum is larger than the previous one. So in this case, the CPU burst time is larger like this one. So it's the same algorithm. Okay. But what about in terms of turnaround time? Do you remember what is the turnaround time? Turnaround time is total amount of time between start to end. So it takes a longer time to finish. Okay? Because shortest job first. Shortest job is optimal for to finish. Okay? However, it's better response time. So that is the round robin. So this slide illustrates the relationship between time quantum size and the context switch we already seen. So keep in mind, the larger time quantum is the same as what? First come, first serve. Okay? Eventually it is the first come, first serve. We will go back one more time during the multi-level feedback queue. So this is the problem. Okay. The next one is priority. So priority, we are going to assign the priority to the process. So it's a general question. When we have the priority 0 to 10, so which one has the highest priority, 0 or 10? 0, 10. In computer, usually 0, lower number is the highest priority. Okay? Why? Is there any reason?
Because it come first. Come first and there is no waiting time.
Somebody may add the next number. If we consider the higher number, the highest the priority, somebody may add 11, 12 like that. So because of that, our goal of assigning priority number is we try to keep the highest priority. So 0 is usually highest priority. Okay? So that is in general, not the computer science only.
One highest priority than 2 and 2 highest priority than 3, that's right?
Yeah, higher the, lower the priority. So from that, so we are going to assign the priority number when the process is created. So each process has the priority number. Then dispatcher will select the process from the ready queue by checking the priority. Okay? So it's a simple implementation. We can consider this is a process list. Okay? Then in the PCB, we are going to add the priority. So this is the current status from the ready queue. Okay? Then we have a CPU burst time, and this one is the arrival time. So it's all this one first come, and the last one is the least come, the latest come. So then using priority, which one will be selected? The process 2 has the highest priority, so P2 will be selected. Then if this one is not preemptive, so this one will be terminated. Then next, this one is done. The 2 is the next one, P5 is selected. Once P5 is done, then the P1 is selected. What if we have the same priority number? For example, we should have the tiebreaker. So most popular the tiebreaker is the first come first serve. So in case, just in case this is a 3 and this is a 3, one. For example, then P1 will be selected as a tiebreaker. So that is the priority scheduling. Also, one more time, any priority-based algorithm, not only scheduling, but the priority, we use a lot. So sometimes, even though we do not intend, so sometimes we use the priority in our mind, in our daily life, right? So that is a priority-based. But the most of the such a priority has the problem of what? Starvation. What is the starvation? If a process has a lower priority, it may not get the chance to be executed. The same thing. In I have a bunch of books. So I have a priority based on my preference. So I like the sci-fi, but the lower priority is the romance. So I never read the romance if I have the sci-fi book. So how can we address such a thing? General solution, not only the CPU scheduling, general solution of priority starvation problem is aging. Aging means at certain amount of time, so if this book is not selected a week, we are going to elevate the promote to the higher level. If not selected, higher level. Eventually, it will be highest level and selected. So this is the aging. This aging starvation and aging solution will be used in any type of the priority-based algorithm. So it is saying that I read an article several years before, not several, it's almost 10, 20 years ago, when the research center in the University of Berkeley, they tried to retire one Unix system. Then, when they retire the Unix system, there is a really old processes. The computer never been shut down for testing purpose. It's almost a decade running. Then they can find the application program that started the 10 years before. That is never been selected, never been run because of the priority. So it has the lowest priority accidentally, then the never been executed, but it's still in the ready queue. So that may happen. So in the CPU scheduling. What about the Windows? Windows uses this priority base. So when it's a 0 to 15 or 0 to 31. So when you run any application program, your application program will be assigned the normal priority. Normal priority means it's a 7 out of 16 the priority level, and or the 15 out of 32 priority level. You can combine with such a priority scheduling with a round robin. Okay, so you have the list of the processes by arrival time. If we are using the round robin, the P1, P2, P3, P4, P5 will be selected. But if we have the priority, we are going to take turn by what? Priority. Okay, so instead of arrival, so round robin, implicitly we use arrival time to order. But we can use the priority for the order. That will be better in terms of satisfaction, right? Because it's the highest priority. So we'll take the first. So, for example, P4, time quantum is 2, but it is selected again. Why? Because it has the highest priority, then it will be selected. In case the same priority, they will take the time. Okay, so this is the another variation of the CPU scheduling, the priority-based scheduling with the round robin. Okay. The next one is a multilevel Q. So far, our Q for the ready the state is only one. So for your quick reminder, we have the new, ready, and running, and terminate the wait. So this one, dispatcher will select the process from the ready queue to the running. So how many queue? We have only one queue. However, so think about the type of process. So if you see the list of processes in your the computer, so we can see the bunch of processes. Roughly when I check the MacBook, it has around 300, 400. You can use top, or you can use the PS, then check how many processes are running. So it's around 400. Then we can quickly classify such processes as the system processes versus application processes. So system process means is when you start up your operating system, the init process, kernel process start the system service processes. On the other hand, the application process is the what? I want to use the computing resource right away. Okay, like MS Word, Microsoft Word, the PowerPoint, or the email. So these are the application process. So we can divide. For example, the process as a background is a service process, or the foreground interactive process. So we can divide the processes by using the characteristic. By the characteristic, we can divide. So for example, foreground need the quick response time. What is the which algorithm provide the quick response time? Round robin, right? So we have simple round robin. So which algorithm provide the turnaround time? The better turnaround time. First come, first serve. So depending on the type of process, can we apply the different algorithm? So to do that, why not? Managing instead of one ready queue here, we are going to add another queue. So this queue is used for foreground process, application process. This one is used for the system process, background. Then we are going to apply the round robin for this. And on the other hand, the background processes, we are going to assign one. Different algorithm, like the first come, first serve. Then we are going to run the different algorithm for better satisfaction. But problem is, here, so we have how many level? Multi-level Q. So that is the reason this is called the multi-level Q. However, if you have the two CPU or two core, so one core will be used for this, another second core used for this, then no problem, right? However, if you have only one core, single CPU over here, timeline is one. How can you manage the two scheduling algorithms? So that is the reason. If you have so multi-level queue looks good. It can consider the characteristic type of processes. We can apply the CPU scheduling algorithm for better performance. However, if you have the single core, single processor, you need to divide the CPU time first. So this one is for the round robin. This one is the first come, first serve. Round robin, the first come, first serve, like this. Or even you can apply the scheduling algorithm first along the number of queue. Okay? Then each round selected, you can apply the CPU scheduling algorithm for each. Okay? So this multi-level queue is the best when you have a multi-core. Okay? Or the multi-CPU. Okay, there is another problem of using the multi-level queue. Anyone? What would be the problem of the multi-level queue? How do you know which one is the foreground? which one is background. I just saying the system processes, or when I click this application process, sometimes it's not clear which one is the system process, which one is the application process, which one is the foreground, which one is the background, which one is the interactive process, which one is the batch process. Sometimes it's not clear to assign. Okay? Just like when you assign the priority, how do you know? Every time, are you going to assign the priority for each process? What if the system processes? So sometimes it's hard to decide the type of the processes. So we are going to address such a thing in multi-level feedback queue. So that is the difference. So multi-level feedback queue. So in a multi-level queue, we are going to schedule along the number of queue. Then assign the specific CPU scheduling algorithm for each queue. Multi-level feed. However, that such a multi-level queue, we need to decide which one is the foreground, which one is the background. In other words, the characteristic should be defined by the user. So which is not practical. So multi-level feedback queue. So we can do this one. You can along the queue you can divide the priority. You can apply any algorithm, CPU scheduling algorithm, so on. So this is the typical example of the multi-level queue. So highest priority means it's almost a real-time processing. Lowest priority is a batch job like this. So you can, if there is a new process is coming in the new state, then for the ready queue, each one has a ready queue 1, ready queue 2, ready queue 3, and so on, number of ready queue. So you need to decide, when I'm saying operating system, decide. So this one goes to the interactive processor, ready queue 3. Or this one goes to the real time because it's important. So this is the multi-level queue, then the number of queue will be selected. At this time, if you have the multiple CPU, multi-core, so each core, core 1, core 2, core 3, core 4 will work for this. If you are using the SMP, symmetric massive processor, so operating system take care, even they are going to consider balancing. Load balancing.
Professor,
yes.
What's the difference between processes that will be in the real-time processing and the interactive processing?
That is from the user point of view. Okay. So interactive, for example, the lower priority usually is they are considering the turnaround time. Short turnaround time is more important than response time. On the other hand, the real-time process means it's a short response time is more important. Usually, this one is the batch job, like the long running job, like the data analytics, okay, or the backup. But the real-time process is the mostly application program that need a quick response time, like the web application or the banking transaction, like this. It's a very subjective. So that is one of the problems. Who decide? Does the operating system know the characteristic of it? Or the programmer, the hard code, the type of so it is hard. So that is a multi-level queue. So we are going to address that in the multi-level feedback queue. So multi-level feedback queue is similar as the multi-level queue, like this one. So let's see, let me use this one. So there are 3 queues. 1, 2, 3. Okay? In a multi-level queue, so input 1 queue, output. So you cannot change the queue. If one process is assigned 1 queue, you should use. There is no inter the queue process. You cannot jump to another process. But the problem is once you assign the process to the specific queue, it's not easy. Once assigned, the process should be terminated in that queue. But to address that limitation of the multi-level queue, so we are going to set up a number of queue, like the multi-level queue. But we are going to use the round robin for each one. So you can see quantum 8, quantum 16. First come, first serve is also round robin, as we discussed before, right? The quantum size 1000, for example. Very long quantum size means what? It's a first come, first serve. So it's the same. So we are going to use the quantum, different size of the quantum around the queue. Then, this one, the shorter quantum, so first queue. So let's say that this is a Q1, this is a Q2, so this is a Q3. So Q1 has only ready queue. Okay, so all processes coming to this queue, Q1. Then we get at least one round of CPU, quantum size 1, 8. If the processes, the CPU burst time is short, they will be terminated, like the what? Real-time processing, or the fast response time process will be completed in first queue. If any remaining job, it will move to the next queue. That has the longer quantum size, like the, for example, 16. 16. Then if this round, if the process is terminated, completed, and terminated. However, if there is any remaining job, remaining CPU time, then move to the next one, Q3. Q3 is the first come, first serve, non-preemptive. So, which means it will be terminated over here. So, when you have a process always enter the short, the quantum size, the round robin queue. If that is the small, the process will be completed here. Otherwise, it will move to the next one, and it will move to the next one like this. So we don't have to worry about the type of the processes. Instead, depending on the CPU burst time remaining, it can move to the next level. The first queue is the real time, for real time processing. The last level means it's a batch job, long running job. So we don't have to worry about the type, characteristic of the process. Instead, we are going to use a multi-level, but it's the output of the one queue will be the input of the next queue. So this is called the multi-level feedback queue. Okay. Just like the multi-level queue, if you have only one CPU, one core, you need to schedule along the queue. Ideally, if you have the multiple queue, that will be better. Okay? And also, for each, we don't have to assign the specific the algorithm. Instead, we are going to use a round robin, because round robin, so it provides a fast response time with a short amount of the quantum. Also, round robin is like the first come, first serve if you increase the quantum size. So when you use the multi-level feedback queue, so you can take care of the different types of the processes. So this is called the multi-level feedback queue. Benefit, I already explained. It's good for the different types of the processes. Then you don't have to explicitly assign the time. The problem, it's getting complicated, right? It's not really rocket science. If you take a look at algorithm itself, it's still much complicated than what? First come, first serve, round robin. Is this the critical? Is this the problem? Yes. Why? Our scheduling algorithm should be simple. It runs the millisecond level. In 1 second, at least 10,000 times of the execution of the CPU algorithm, CPU scheduling algorithm. That is the reason CPU scheduler sometimes the process number ID 1. Some of the operating system use the SCHED. It's a scheduler, daemon process. So it should be fast and simple. But multi-level feedback queue, as you can see, this is a couple of times I assigned this problem as the programming project. So it doesn't look like the first time the simple, but eventually simple actually. So how many different scheduling algorithms do you need to implement? How many? Only one. Actually, round robin. If you implement the round robin one, then it's a simple one. You need to manage the input and output and so on. So it's considering the complexity level. So it's much complex than the other algorithm. That is the drawback. But still, it's used in the operating system because it can take care of the different types of the processes. Let me show you the. I have the yes. So can you see the project 1? Yeah, okay, thank you. So this is the illustration of the multi-level feedback queue that I have used for the project several years before. So for your better understanding, I'd like to use this one, okay, as an example. So we are going to implement the multi-level feedback queue here. So there are 3 queues. So 3 linear queue. One is Q0, then Q1 and Q2. Okay, Q0 is round robin with the time quantum 8. The Q1 is round robin with the time quantum 16. Then the Q2 is actually round robin with the time quantum 10,000, for example. It's the first come first serve. So when I grade this one, I actually grade first whether the student implement the first come first serve separately or not. You don't have to implement the first come first serve separately. Just a round robin, but the input parameter quantum size is very high, reasonably, so like a million, like that. Then it is the first come first serve. Then scheduling rule, okay. The Q0 is the highest priority, which means it's real time, and the Q2, first come first serve, is the lowest priority, like the batch job. And the new process coming in the Q0, like here, and then, so enter here. If terminated, terminate, and otherwise move to the next queue and quantum 16 and terminate. Here is all these are the terminate. And if not, going to the third queue, and eventually it will be terminated, like this one. This is the architecture. And in your PCB, process control block, you need to manage the process ID, and arrival time, and CPU burst time, and the queue number also. You should know where is the queue, where is the process. Each queue, the process is, okay? You can create the process, the CPU burst time randomly, like this. So this is the example. So we have the processor list like this one. This is our expectation. So arrival time 2, 8, and the CPU burst time with 10, 7, like this. So at time 0, no process alive. So empty, all of this. So in the Gantt chart, it says nothing. Then if the time is 2, time 2 P0 is alive with the CPU burst time 10. So then take a look at both the Gantt chart as well as the Q. So Q0, what is the time quantum size of the Q0? It's 8, right? So let's go back once again. 8, 16, and the first come first serve. So P0, question. P0 can be terminated in the Q0 or not? It's no. So which means this one at time 10 move to the Q1. Okay, move to the Q1. So, but meanwhile at time 8, new process coming in. But at least the P0 will take the time quantum 8. So still the P0. So that is the reason it's also a good idea. Which one is the running? You can manage the running state. So that the time 10, the P0, the remaining CPU time is 2, so it will not go to the terminate and it will move to the next. Okay, then until time 10, the two process P1 and P2 is alive. So this is the first come first serve. This is the first come and first serve, then round robin. Only one round. So then this time, this is the one tricky part of this project. We have the one CPU in this, one core, one CPU. So you need to schedule along the one, the queue. So we apply the simple. So this one is the priority. So 0, 1, 2 priority, which means if there is any process in the highest priority, will take the CPU resource. But you can consider different way. Like this one is 60%, this one is 20%, this one is 20%, and round robin. Or you can take the any. But to simplify the problem, I asked the priority based, the algorithm for this. So which means because there is a process, the Q0 will take the CPU resource. Because of that, Q1 doesn't work anything. So keep going. So once the Q0 is done, where is the P1? P1 is only need 7. So within the first Q, it is terminated. Okay? So we don't have to consider the type of process in multi-level feedback queue. If it's short CPU burst time, which means it's the quick response time, the needed, so it will be terminated. So we can continue this one. Then we can follow. You can find this slide from the canvas, so you can just the slide show. Then you are able to understand idea of the multi-level feedback queue. Also, as I suggest, whenever you see such the algorithm, first you need to understand the algorithm and think about, if I need to implement this algorithm, how can I? So for example, in this kind of example, so you need to have the data structure for PCB for each process, and also the process list, and also manage the queue. How many queue? 3 queue. Then in your main program, you are going to run your algorithm with the while loop. So one loop will be what? One time slot. Okay? One loop will be one time slot. In real implementation, every timer, then the scheduling algorithm scheduling process will be the run. But in your implementation, you may use the while loop, and every loop, every iteration means indicate the one time slot. Then you can do that. Also, in your program, definitely you need to manage this Gantt chart. How can you manage the Gantt chart? In your PCB, what is the waiting time? What is the response time? What is the time? Then later you can evaluate also. Let's keep going. So I don't want to explain each step by step. You can just see the illustration. Then P4 is coming. So because there is a process in Q0, P4 will get the CPU resource. Still the Q1 has that. And then P5 coming. And after the round like this, then the P2 get the 2 times log, but unfortunately there is another process Q0, and we'll take this and this, and P2 finally completed. And the P3 is there, and but the P8 is alive, and so on. Then the P9 is completed, and P3 is completed, terminated, but P5 still is not terminated, because P5, as you can see, it needs 28. So it will be terminated once there is no the process in the lower highest queue. Like this, finally, it is terminated like this. Then you are able to analyze using the recorded track the information on your PCB, what is the waiting time, what is turnaround time, what is the response time, and so on. Okay, so let me close this. And share the slide for this. Okay, so this is the multi-level feedback queue. Okay. So far we have discussed about the scheduling with the assumption of what? The processes. What about the thread? Nowadays more and more thread are using. So thread should be scheduled. There are 2 types of the thread, the scheduling. One is, think about this is the computer and operating system. You may have a number of threads. So sometimes you have the user thread, the user create the thread. Sometimes you have the kernel thread, so your operating system create the thread. So system-wide, entire operating system, your operating system managed a number of threads, then schedule. So this is called the system contention scope thread, sometimes in short the SCS. However, as we discussed in chapter 4, each process may create the user thread and also the kernel thread. So operating system actually assign the CPU resource using their whatever the CPU scheduling algorithm. Then within that, the running state, each process also schedule for along the thread that process create. Okay, so this is called the process level thread. Process level scheduling, or the process contention scope (PCS). So there are 2 types of the thread scheduling: system-wide thread scheduling, and process-wide scheduling. But as you can imagine, this system-wide thread scheduling will be used for mostly kernel thread. So user is not in charge of the kernel thread. Only the operating system is in charge of that. Because of what? It's the dual mode, user mode and the kernel mode. If we give the permission for user process, user application to control the kernel thread, it will be the problem. Also, there is the process contention scope. Process level mostly focus on what? User thread. So user thread, you are able to schedule, thread level scheduling. Okay. So P-thread, for example, POSIX thread provide both the PCS and SCS. So this is the example of the P-thread scheduling API. So you can see the scope. You are going to decide the scope. So P-thread underscore the score underscore process is the process level. Okay. And this one is the P-thread system is the operating system level. Okay. So you are able to select in your API which thread scheduling algorithm will be used. Then finally you can run the thread programming with either PCS or SCS, the scheduling algorithm. So far, it's okay. So it's a thread programming. What if we have the multiple processor? it will be really complicated. So that is the actually main part of the SMP machine. So symmetric massive processes, when you have the multiple processor, to support the massive multiple processor in your operating system, then the user application doesn't have to worry about the scheduling or whatever, only the operating system that take care. Then maximize the utilization and best performance. So nowadays most of the personal computer is a multi-core system. So it's similar as the multiprocessor. So multi-core, so we will see the idea of such a multiple processor scheduling. There are two types of that. One is we are going to assign the thread or processes to the specific core. So if this one is the ready, and go back to here. So each core has their own queue. On the other hand, the operating system manages one common queue. Then depending on the status of each core, one is not busy, then select the process here from the common queue. So there are two types of the scheduling. Okay. And in the multi-threaded, the multi-core system, we are going to run the thread for each core. So then we can get the best performance of the utilization of the CPU. So this is the idea of the illustration of the multi-core system that supports the multi-threaded program. Okay? So you can see the thread for each core. Okay? So it's a hardware level, the threaded programming. So like for example, hyper-threading is supported by the Intel and so on. So one of the such an example is if you are using the virtual machine. So virtual machine needs the hyper-threading. So if you are not going to enable such a hyper-threading, hardware level threading, sometimes the virtual machine VMware or the virtual box will not work on your Windows system. I think that this one we already discussed during the thread. One of the issue of the thread is we have a number of the user thread and number of the kernel thread. So we need to, this one is called the lightweight processor. So LWP need to schedule to assign the between the number of user thread and number of kernel thread. So that is the LWP, the thread, the processor has the scheduling. Specifically, if you select the PCS, the process level, the thread, that the LWP will be in charge of the thread scheduling. When you have the multiple process, there are two types of. So let's say this is the CPU or the core. Then, there are two types of the migration. Migration means this one is busy and this one is not busy. So it has the idle, 100% the 0% usage. So this one can take care get the thread or processes. But if the one has their own queue, each CPU or the core has their own queue, there's nothing. So at the time, there are two types of the migration. Migration means move the one process to another processor. So push migration is each process, if I'm busy, then the push out the process to another one. On the other hand, if I'm the idle, I can take the processes, then get pulled out the processor from the other. Okay, this looks like the simple, but actually it's overhead because each processor has what? The memory. L2 cache, L1 cache and L2 cache over here. Once it is migrated, all the information about the memory should be migrated. It takes longer time. So even though the CPU is idle, so it's, you want to balance, but when you migrate, so you need to move all of the cache information. So that is the reason nowadays we consider the affinity. So you'd better to keep the process in the same processor, the core. So if you you will not allow such a migration, that is called hard affinity. However, hard affinity, you cannot maximize the utilization. So soft affinity is operating system try the best to keep the same core, same process. But in case the load balance, we can migrate. That is the soft affinity. So to address that, there's a new architecture. It's not new architecture. IBM provide a NUMA architecture, non-uniform memory accessing. Meaning is, even CPU can access the memory. This time memory means cache. Okay, L1 cache and L2 cache. It can access the cache in the another CPU. But this time it takes the time, so slow access. This one definitely in the same mode, the memory is faster. But it allows. How can you make this one? At that time you can connect there's a memory channel between the processor. So this memory channel definitely slower than in the same chip. Okay? But this one is really fast one. It's a lot faster. It's faster than the bus speed, but it's slower than the same chip. But it allows to access. It's as name implies, non-uniform. Uniform means the CPU access the data in the same chip, but it allows to access another one. So this one is called the NUMA architecture. Nowadays, NUMA architecture is used a lot for such as the SMP architecture. But if we have such a NUMA architecture, we can easily implement such a soft affinity for with the migration. So next one is the real-time CPU scheduling. The other part is much simpler than the CPU scheduling. So I'd like to, because we have only the 3 minutes, I'd like to introduce what is a real-time scheduling. So what is a real-time? So real-time processing, real-time system. What is the meaning of real-time when we are saying the real-time in computer and computer science?
It's more like, say, while the user is, say, giving some sort of input, being processed like at that very same time and they're getting the result.
Same time. That's the common idea of the real-time, or it's very fast. However, in computer and computer science, real-time does not mean, actually implicitly we expect the fast or the same time processing, but same time practically not possible, right? So think about when you send the data through the network, is it possible same time receive? There is always a delay, latency. The problem is how much make the latency smaller and smaller, but still there exists a latency, which means we cannot make the really real time. It's not possible. Then fast means it's less latency. How much fast? We don't know. So instead, in computer science, when we are saying the real time, means it's a guaranteed time. So like the service-oriented architecture, so we are going to guarantee the process will be completed within 10 seconds, like that. This process will get the CPU resource, response time is less than 1 second. Like the service scope, then we guarantee. That is real time. Then what is the benefit of the real time? We can do something, we can make a plan. Like I think about maybe 10 years ago, there is a Fukushima, the tsunami hit the nuclear plant, right? So they should definitely have the real-time alert system. However, it is not possible. Really, same time tsunami coming, then the same time warning is not possible. But their real-time means within a minute, no matter what happened. So within a minute, alert. Okay, send out the broadcast signal to the people within a minute or within 10 minutes. For example, 10 minutes. So if you give the 10 minutes, so within a 10 minutes, if you alert to the people get evacuated. That's a plan. Then the government can make the plan for the evacuation zone. The faster, the better, but when we are saying the real time means it's a guaranteed time. So a lot of mission critical systems need such a real time CPU scheduling. In other words, it's called the real time operating system. Like the robot, if a robot controls all the humanoid robot, so we have the 30 different motor, the controller should be real time. Otherwise, you cannot balance. If one motor is slower, the other are faster, you cannot balance. So you cannot implement the kinematic operation. So within 10 milliseconds, all motors should be response. Then you can make the robot to work like that. So that is a real-time, the CPU scheduling. We will see how to guarantee the response time of the CPU in the next class. Then we'll continue for the CPU process synchronization in next week. So the exercise lab is not posted yet. It will be available by the end of tonight or tomorrow. Then you can watch the video. Okay. Thank you, and we will see you next week.